Hello there, and welcome to Calm Science for Sleep, where the night is long enough to hold a question this large, and where nothing has to be understood tonight in order to be enjoyed. Tonight, we're going to ask something that sounds simple and isn't. What is the largest thing in the universe? There is a candidate. I'll give it to you before we finish. It's a proposed wall of galaxies about 10 billion light years across, wide enough that light, the fastest thing there is, would need nearly 3/4 of the age of the universe to cross from one end of it to the other. And astronomers are still arguing about whether it is really there. That argument is not a footnote. It's the most honest thing about tonight's question, and I'd rather tell you now than let you find out at the end. By the time we reach the top of this ladder, you'll have two answers: the largest structure we can confidently describe, and the largest one anybody has claimed. They are not the same object, and the gap between them is where the interesting part lives. Either way, the number on its own is almost useless. A figure that size doesn't land anywhere. It just sits there, too big to feel. So, we're not going to start at the top. We're going to climb toward it. 20 steps, each one larger than the last, beginning with something you are standing on right now. And before the first step, two problems worth admitting out loud. The first is the word largest. Widest across? Heaviest? Taking up the most room? Or reaching furthest, even when there's almost nothing there to touch? Each of those walks off in a different direction and arrives somewhere else. The second is the word thing. Tonight's ladder does not climb through 20 objects of the same kind. Some rungs are objects you could point at. Some are boundaries, the edge of where a star's wind still wins. One is a spacecraft. One is a hole with almost nothing in it. The ones at the top are patterns in how matter is spread, rather than lumps of it. I'll tell you each time the kind of thing changes, because that shift is half of what the climb is actually teaching. Neither of those is a flaw in the question. They are the whole reason it takes a night to answer. Before we begin climbing, though, where are you listening from tonight? Maybe you're in a dark room with one small lamp still on. Maybe you're already in bed, with your phone resting somewhere beside you. Maybe you're half here and half gone, and my voice is only the thread keeping you tied to the waking world. Wherever you are, you're somewhere inside the thing we're about to measure. There's no standing outside it. If this slow way of wandering is useful to you, a like or a subscribe helps this quiet corner find the people who need something gentle at this hour. And if you'd rather not, that's completely fine. The universe has been patient for a very long time. We can be too. So, the largest thing in the universe. We start with the one lamp you have ever stood inside. Earth is 12,742 kilometers across. That number means very little until you try to walk it. The distance around the equator is a little over 40,000 kilometers. Walk 8 hours a day, every day, at an ordinary pace. No oceans, no mountains, no days off, and you would need close to 3 years to arrive back where you started. Not a trip. a significant portion of a life. For almost all of human history, this was the whole stage. Everything anyone had ever loved or feared or built was somewhere on that surface, and the surface felt endless because the horizon keeps its distance no matter how long you walk toward it. And on that stage, the giants were obvious. Everest rises almost 9 kilometers above the sea. The air at the summit holds about a third of the oxygen your body expects. Every step costs something. People carry bottled air up there simply to stay alive long enough to look around. The Mariana Trench runs the other way, nearly 11 kilometers straight down. Drop Everest into it, and the peak would still sit more than a kilometer underwater, in a darkness where the pressure would crush a submarine like a paper cup. These are the largest things a human being can stand next to and feel small beside. They earned the word giant honestly. Then, in December of 1972, the crew of Apollo 17 looked back from about 29,000 kilometers away and took a photograph. In that single frame was the entire stage. Every ocean, every mountain range, every person alive, and every person who had ever lived. All of it fitting inside one circle of blue and white, small enough to cover with a thumb. And here is what that photograph quietly did to the giants. Shrink the Earth down to the size of a billiard ball, and Everest, the wall that takes bottled air and weeks of climbing, becomes a bump 0.04 of a millimeter high. That's smaller than the tolerance a billiard ball is manufactured to. Which means, at that scale, you could roll our planet between your fingers and your skin would find nothing at all. No mountains. No trenches. Smooth glass. The giants didn't get smaller. You just stepped back far enough to see what they were the whole time. That's the first rule of this climb, and it will hold for every step after. Large is not a property a thing owns. It's a relationship between the thing and wherever you happen to be standing. And we've only stepped back once. Because this entire world, every ocean, every summit, every person, could be dropped into the next object on the ladder more than 1,300 times and still leave room. More than 1,300 times. That's Jupiter. 139,820 kilometers across, about 11 Earths laid side by side to span its face, and 1,300 Earths to fill it. Hold that for a moment, because the number hides how strange it is. Jupiter is not a bigger version of the world you live on. There is no surface. There is nowhere to land. There is no line anywhere on that planet where you could say, here is where the sky stops and the ground begins. Let yourself fall toward it for a moment, since falling costs nothing tonight. You would pass first through ammonia clouds, pale and cold, the ones that give the planet its cream and rust-colored bands. Below them, the pressure begins to build. The air thickens around you until it isn't air anymore. It's a fog too dense to move through, then a fluid too hot to name. Deeper still, the hydrogen itself gives up being a gas and starts behaving like a metal, conducting electricity in a churning ocean tens of thousands of kilometers deep. And somewhere far below that, perhaps, a rocky core the size of several Earths, which no instrument has ever seen and which may not have a firm edge either. At no point in that entire descent do you arrive. You just keep going until the planet stops being a place and becomes a pressure. The clouds themselves run in bands, pulled into stripes by winds that never stop. And set into those bands is the storm. The great red spot is a single weather system wider than the entire Earth. Not a season. Not a hurricane that spends itself in a week. A storm that astronomers have been watching on and off since the 1600s, and which has been turning continuously in our records for something like 190 years without a break. Try to feel the length of that. The worst storm you have personally lived through lasted hours, perhaps a day. You remember it because it was extraordinary. On Jupiter, the extraordinary has been going on since before your great-great-grandparents were born, and nothing about it suggests urgency. It simply turns, slowly, counterclockwise, in a planet with no ground to blow across. It is also shrinking. Measurements over the last century show the spot narrowing from something that could once have swallowed 2 or 3 Earths side by side to something that now fits roughly 1. Even the longest storm we know of is a temporary arrangement. It's simply temporary on a scale that outruns us. Jupiter carries a small kingdom with it too. 95 confirmed moons at last count, and among them, worlds that would be planets anywhere else. Ganymede is larger than Mercury. Europa hides a saltwater ocean beneath its ice, holding, by some estimates, more liquid water than every ocean on Earth combined. That's a strange sentence to say out loud in a quiet room. The most water we know of, anywhere besides here, is sealed under the crust of a moon orbiting a planet with no floor. And around all of it sits a magnetic field so powerful that it traps radiation in belts lethal to anything unshielded. That same field paints permanent aurorae over both poles, curtains of light hundreds of times brighter than the ones that occasionally reach our own polar skies. Jupiter glows at its poles all the time. Nobody is ever there to see it. So Jupiter is enormous by every measure we've used so far. Wider than 1,000 Earths could fill. Heavier than 300 of them. Loud with storms that outlive nations, ringed by oceans nobody has touched, crowned with light nobody watches. And it is, in the only way that matters tonight, not a star, and it was never close to being one. That last part is worth saying carefully, because Jupiter is often described as a failed star, and the phrase does more harm than good. It has roughly the right ingredients, mostly hydrogen and helium, the same material stars are made from. What it does not have is anything like enough of itself. To begin fusing hydrogen in its core, Jupiter would need to be around 80 times more massive than it is. 80 times. Not double. Not 5 times. To call that a near miss is like calling a puddle a failed ocean. So it sits there, the largest thing in our neighborhood that isn't the sun, made of star material and doing nothing whatsoever that a star does. It has the ingredients. It has the depth, the pressure, the heat by planetary standards. It has a wick's worth of everything and never once had a flame. It is a lamp with no wick. It holds oil enough to burn for eternity and gives off nothing you could read a page by. And that failure is not a small detail. It's the entire reason the next step is the size it is. Because the thing Jupiter failed to become is sitting right there in the middle of everything, and it has been burning without pause for every second you have been alive. If you want to know what Jupiter was reaching for and missing, you don't need a telescope. You only have to step outside during the day and feel your own skin. Feel your own skin. That warmth arrived 8 minutes and 20 seconds ago, from a distance of about 150 million kilometers, and it is the single most reliable fact of your life. It was there before you were born, and it will be there long after. You have never once had to check whether it was still working. The Sun is 1,392,700 kilometers across. That's 109 Earths, laid edge to edge, just to reach across its face. To fill it, you would need about 1,300,000 of them. And every single one of those Earths would contain every ocean and every mountain and every person we talked about at the start of the climb. But the number that reorders everything isn't width. It's share. The Sun holds 99.86% of all the mass in the solar system. Everything else, Jupiter with its failed ignition, Saturn, the ice giants, every moon, every asteroid, every comet, and this world beneath you, everything else divides the remaining fraction of a percent between them. Which means that, honestly stated, the solar system is the Sun. The rest of us are rounding error, held in place by something that would not notice if we stopped. And here is what it's doing while you lie there. Every second, the Sun converts about 600 million tons of hydrogen into helium. In that conversion, roughly 4 million tons of matter simply stops being matter and leaves as energy. 4 million tons. Every second. It has been doing this for 4.5 billion years and holds enough fuel to continue for about 5 billion more. The light that reaches your window has a longer story than that, though. A photon born in the core doesn't fly straight out. It's absorbed and re-emitted, over and over, staggering through material so dense it can travel only a hair's width before something stops it again. By the time it escapes the surface, tens of thousands of years may have passed. The warmth on your face left the core before there were cities. Before there was writing. It only took 8 minutes for the last leg of the journey. The surface itself sits at about 5,500 degrees Celsius, hot enough to vaporize any material we could build from. And then, strangely, above that surface, the temperature goes up. The outer atmosphere, the corona, reaches over 1 million degrees, and nobody has entirely settled why. The layer furthest from the fire is hotter than the fire. It's one of the oldest open questions in the study of our own star, sitting there, in plain view, unresolved. The Sun has weather too, though it doesn't look like ours. Dark patches drift across the surface, sunspots, cooler regions where magnetic fields have knotted themselves tight. A large one is comfortably wider than the Earth. They come and go on a rhythm of roughly 11 years, and when the magnetic knots snap, the sun throws material outward, flares of radiation, and slower eruptions that fling billions of tons of charged particles into space. Sometimes, that material reaches us. When it does, it strikes the magnetic field wrapped around our planet, and the sky at high latitudes fills with green and violet light that shifts like a curtain in a draft. People stand outside in the cold to watch it and call it beautiful, which it is. It is also the visible edge of a storm that began on a surface 150 million kilometers away. This is the first true lamp on our ladder. Everything before it borrowed light. This one makes it. And yet, if you gathered the stars of our galaxy and sorted them by size, the sun would not stand out. It's classed as a yellow dwarf, a description that sounds almost dismissive and is accurate. Most stars in the galaxy are smaller and dimmer than ours. A meaningful number are hundreds of times wider. In that crowd, our sun is middling, unremarkable, the kind of star you would pass over without comment on a chart. There is something quietly steadying in that, if you let it settle. The thing that makes every living moment on this planet possible, every leaf, every breath, every warm afternoon you have ever fallen asleep in, is, by cosmic standards, an ordinary object. Not chosen. Not rare. Just close. But close is doing enormous work in that sentence. Because when a star is far enough away, size stops being visible at all. Distance flattens everything into the same small point of light. And there is a star you have almost certainly seen with your own eyes, hanging on the shoulder of the most recognizable constellation in the sky, that is so much larger than the sun that the comparison stops behaving like arithmetic. It looks like a dim orange dot. It is not Betelgeuse. Go outside on a winter night in the northern hemisphere and find Orion, 3 stars in a short, straight row, the easiest pattern in the sky to learn. Then look up and to the left, at the hunter's shoulder. That orange star is Betelgeuse, and it sits about 548 light-years away. Its diameter is roughly 764 times the diameter of the Sun, not 764 times heavier, wider. 764 suns laid in a line just to cross it once. Here's what that means, in the only terms that will land. Take Betelgeuse and set it down where the sun is, with its center exactly where the sun's center sits. Mercury is gone. Venus is gone. Earth is gone, not scorched, simply inside. Mars is gone. The star's surface would extend out past the orbit of Mars, into the region where the asteroid belt drifts, and every world you have ever heard the name of would be somewhere within it. The entire theater of the last 3 chapters, the walk around the equator, the storm wider than a planet, the 8-minute journey of light to your skin, all of it fits inside a single star, one you can find from your driveway without a telescope. And that star is dying. Betelgeuse is enormous because it is dying. That's the part worth slowing down for. A star spends most of its life in balance, gravity squeezing inward, fusion pushing outward, the two forces holding each other in a truce that can last billions of years. When the hydrogen in the core runs low, the truce breaks. The core contracts and heats further. The outer layers are pushed outward, and the star swells into something vast and cool and unsteady, the surface so distended that its grip on its own material becomes weak. The size isn't strength. The size is a symptom. It's also the reason measuring these stars is genuinely difficult. A supergiant doesn't end at a clean edge. Its outer layers thin out gradually into the surrounding space, so the answer to how wide is it depends partly on where you decide the star stops. The figure of 764 solar diameters comes from careful modeling published in 2020, and it revised earlier numbers that had been quoted for years. This is normal. It is also worth saying plainly, because a number repeated confidently for a decade can still turn out to be provisional. Even its distance is not fully settled. Published figures for Betelgeuse have ranged over a span of more than 100 light-years, and since the calculated size depends directly on the assumed distance, every revision to one moves the other. The star is close enough to study in detail and far enough to remain slippery. What makes it measurable at all is a technique called interferometry, combining the light from several telescopes to act as one much larger instrument. It's the same principle that will matter enormously later tonight, on a rung near the top of this ladder, for a very different reason. Betelgeuse was one of the first stars whose disk was ever resolved that way. Not a point of light. An actual surface, with uneven patches on it, convection cells the size of our entire planetary orbit, rising and sinking on a surface so vast that a single bubble of gas takes years to complete one turn. We watched this star become unpredictable recently, in a way nobody expected. Beginning in late 2019 and continuing into early 2020, Betelgeuse began to dim. Not slightly. It faded to roughly a third of its usual brightness, enough that people who knew the winter sky noticed with their own eyes that Orion's shoulder looked wrong. For a few months, a serious number of people wondered whether they were watching the opening act of a supernova, an explosion that at that distance would have been visible in broad daylight. It wasn't. The star had ejected a cloud of material that drifted across our line of sight and cooled into dust, dimming it the way breath dims a window. Betelgeuse brightened again over the following months. But the lesson stayed. Something we had drawn on star charts for thousands of years, something sailors navigated by, something people had assumed to be simply there, turned out to be shedding pieces of itself in front of an audience. When it does finally collapse, it will be one of the brightest objects in our night sky, possibly bright enough to cast shadows. And the light that shows us will have left 5.5 centuries earlier. Which means the explosion may already have happened. The message may already be somewhere in the gap between us, crossing dark space at 300,000 kilometers a second, and there is no method by which we could know. That thought sits oddly well at this hour. Somewhere out there, a thing may already be over, and we are still living inside the last moments of the old news. This is a lamp with the oil running out, flaring wide and orange and unsteady, throwing off pieces of itself in what passes for a final gesture on a stellar timescale. And still, it is not the largest star, because a lamp can swell further than this before the fire loses hold of it. Not much further. But further. In the constellation Scutum, there is a dense knot of red supergiants discovered in the 1990s and catalogued without ceremony. The 18th object on that list carries a name nobody would choose for something this size. Stephenson 2-18. Its diameter is estimated at around 2,150 times the diameter of the Sun. Put it where the Sun is, and this time the erasure doesn't stop at the asteroid belt. Mercury, Venus, Earth, Mars, inside. The asteroid belt, inside. Jupiter, with its 1,300 Earths, and its centuries-long storm, and its hidden ocean moons, inside. The surface of this star would reach out to roughly the orbit of Saturn before it finally stopped. Every step we have climbed tonight, the walk around the world, the lamp with no wick, the burning one, the dying orange giant, all of it fits within a single object, with room left over. Take a breath there, because it's worth noticing what just happened to the latter. We began with something you could walk around in 3 years. 4 steps later, we're describing an object where light itself needs hours to cross the distance from one edge to the other. And we are still in the same galaxy, still looking at a single star, still 15 steps from the top. And here is where the climb runs into a wall, which is exactly what earns this step its place. Stars cannot keep getting larger. There is a ceiling, and Stephenson 2-18 is pressed against it. Current theory puts the practical upper limit for a red supergiant somewhere around 1,500 times the Sun's radius. The fact that our best estimate for this star exceeds that limit is not a triumph. It's a flag. Either the estimate carries more uncertainty than the headline number suggests. Distance measurements to objects this far away have real error bars, or the star is doing something our models don't fully account for. Both are honest possibilities, and it would be dishonest to pick the more dramatic one just because it sounds better at this hour. That uncertainty isn't a weakness in the story. It is the story. It helps to know how a measurement like this is actually made, because it explains why the error bars are so wide. Nobody can see the disk of a star this distant. You get a point of light. Its color gives you a surface temperature. Its brightness gives you an output, and if you know the distance, those two together give you a radius, because a cooler surface has to be much larger to emit the same energy. Every link in that chain has slack. The distance is uncertain. The star is wrapped in dust that reddens and dims it, so correcting for dust means estimating how much is in the way. It may not even belong to the cluster it's named after, which is why you will find published estimates for this star that differ from each other by more than the entire diameter of Betelgeuse. None of that makes it small. It simply means the headline number carries a shrug inside it that the headline never shows. There is a second thing happening to a star this size, and it's quieter than the first. It's losing itself. continuously. Stars at this scale shed material into space at rates that would be unimaginable anywhere lower on the ladder. The outer layers are so loosely bound that the star's own radiation pushes them away. Over the last stretch of its life, an object like this can throw off a significant fraction of its total mass into the surrounding dark, wrapping itself in a shroud of the material it used to be. So the largest fire is also the leakiest. It cannot hold what it has. Because what stops a star from growing is not a shortage of material. It's that fire, past a certain size, cannot hold its own shape. The outer layers become so thin and so weakly held that the star begins shrugging them off into space, a slow, continuous loss, tons of itself drifting away every second. It cannot keep what it has. Push harder and the star doesn't get bigger. It starts coming apart. There's something almost gentle in that limit if you turn it over. The universe is not short on material. It could, in principle, gather far more of it in one place. What it cannot do is make fire hold together past a certain width. The ceiling isn't imposed from outside. It comes from the nature of burning itself. So this is the end of one kind of largeness. Somewhere in this neighborhood of scale, we have reached the largest fire that anything, anywhere, can hold. Which means that if we want to go further, and we have 15 steps left tonight, we have to stop asking about fire altogether. The things ahead of us on this ladder are not brighter. Most of them do not shine at all. Some are made of nothing but distance and the memory of light. So the next step is not a larger object. It's the space between objects, the gap our own star holds open around itself. And the man who first measured the far edge of that gap never once looked through a telescope to find it. He worked it out with a pencil. In the 1840s, Uranus had a problem. It wasn't where it was supposed to be. Astronomers had charted its orbit carefully, applied Newton's laws, predicted where it would appear, and the planet kept arriving slightly late, then slightly early, drifting off the calculated path by amounts too small to see with the naked eye and too large to ignore. There were two possible explanations. Either Newton's laws were wrong at that distance, which would have unmade the foundation of physics, or something out there was pulling on Uranus that nobody had found yet. Urbain Le Verrier, working in Paris, chose the second option and did something remarkable with it. He took the deviations, worked backward through them, and calculated the position of an object he had never observed, whose existence nobody had confirmed, using nothing but arithmetic, and the assumption that gravity behaves the same everywhere. Then he wrote a letter with a set of coordinates in it and sent it to Johann Galle at the Berlin Observatory. Galle received the letter on the 23rd of September, 1846. He and his assistant Heinrich de Rest pointed the telescope at the coordinates that same night. They found it within an hour, less than 1 degree from where the letter said it would be. Sit with that for a moment, because it may be the strangest thing humans have ever done with a piece of paper. A planet 4.5 billion kilometers away, unseen by anyone in history, was located because its gravity had been nudging another planet slightly off schedule, and someone noticed and did the sums. There is a second name that belongs here. In England, John Couch Adams had been working the same problem alone and reached a similar answer somewhat earlier, but nobody acted on his figures in time, and no British telescope was pointed at the sky that night. Two people, working separately with pencils, both reached into the dark and found the same invisible thing waiting there. Neptune is 49,244 kilometers across, about 4 Earths wide. It's a cold blue world of hydrogen, helium, and methane, with the fastest winds measured anywhere in the solar system, over 2,000 kilometers an hour, in an atmosphere so cold that the energy driving those winds remains an open question. But tonight, Neptune matters less as an object than as a marker, because Neptune's orbit is the practical edge of the planetary system. It circles the Sun at about 30 times the Earth's distance, which means the full width of that orbit is 60 times the distance from here to the Sun, roughly 9 billion kilometers across. 9 billion. We've been climbing all evening, and we've finally reached a number that needs a new unit to stay readable. Here's what that width feels like, in the only currency this ladder respects. Sunlight, which reaches your window in 8 minutes and 20 seconds, needs 4 hours and 9 minutes to reach Neptune. 4 hours. The same light, from the same source, arriving after most of a working day. And Voyager 2, a spacecraft moving faster than anything humans had built at the time, was launched in 1977 and did not pass Neptune until August of 1989. 12 years. To cross the width of the neighborhood. In the fastest thing we had. There's something worth noticing in what we just measured, though, and it changes the shape of the climb from here on. Every step so far has been a thing. A world, a failed star, a burning one, a dying one. You could point at each of them. This one isn't. 9 billion kilometers of solar system is, by volume, almost entirely nothing. Empty space with 8 small objects and a scattering of ice and rock moving through it, so widely separated that if you were dropped at random inside the orbit of Neptune, the overwhelming likelihood is you would see no planet at all, just the Sun, small and sharp, and the dark. The halo around the lamp is not the lamp. It's mostly darkness, with the lamp somewhere in it. And Neptune is not the edge of that halo. It's only the last thing there, with a name people learn as children. The Sun's actual territory, the region where its wind, its magnetic field, its influence still governs what happens, extends far past Neptune, out into a place no photograph exists of, because nothing has ever looked back at it from outside. Except that isn't quite true anymore. One thing has been there. It left in 1977, and it has been traveling outward ever since, and in 2012, it crossed the line. 1977 and 2012. 35 years between those two numbers, and in the gap sits the longest journey any object built by human hands has ever made. Voyager 1 launched on the 5th of September 1977 on a mission that was supposed to last about 5 years. Fly past Jupiter. Fly past Saturn. Send back photographs. Stop. It is still transmitting. The spacecraft carries a computer with less memory than a modern greeting card that plays a song. It was built with technology that predates the personal computer, the mobile phone, and most of the people listening to this. And it has now been operating continuously for longer than the majority of human careers. For decades, it flew through the region we've been describing, the halo, the vast emptiness holding the planets. Past Jupiter in 1979. Past Saturn in 1980. Then out, with no more worlds ahead of it, into the part of the journey that had no photographs and no arrival date. And on the 25th of August 2012, the instruments recorded something that took a year of analysis to confirm. The character of the particles around the spacecraft had changed. The solar wind, the constant stream of charged particles our sun exhales in every direction, had stopped. In its place was something else, the thin, cold medium that fills the space between stars. Voyager 1 had crossed the heliopause, the boundary where the sun's wind finally loses its push against the wind of the galaxy. That boundary sat at roughly 123 times the Earth's distance from the sun, which makes the full width of the sun's domain something like 246 times that distance, around 37 billion kilometers across, 4 times wider than the planetary system we just measured. That's the honest edge of our lamp. Not where the planets stop, but where the light stops deciding things. And here is the part that tends to sit strangely in the chest at this hour. There is no wall there. No line, no marker, nothing to see. A spacecraft crossed the outermost boundary of everything our star governs, and the only way anyone knew was that the readings changed. The most significant frontier in the history of our species was detected by a shift in particle counts. Voyager is now more than 160 times the Earth-Sun distance away, and still going. A radio signal from it takes over 22 hours to reach us. When engineers send a command, they wait most of 2 days for the acknowledgement. Every conversation with it is a letter posted across a gap where the answer arrives the day after tomorrow. Its power is failing, slowly and predictably. Instruments have been switched off, one by one, to conserve what's left. Sometime in the next few years, the last of them will go quiet, and the spacecraft will continue outward exactly as it is, unpowered and unheard, for as long as there is a galaxy to move through. There is one more thing it did, on the way out, and it was not part of any mission plan. In 1990, with the planetary encounters finished, and the cameras about to be shut down for good, the spacecraft was turned around at a distance of about 6 billion kilometers and told to photograph the place it came from. In the resulting image, the Earth occupies less than a single pixel. A pale dot caught in a band of scattered sunlight, indistinguishable from a speck of dust on the lens, unless you know exactly where to look. Carl Sagan had argued for taking the picture, over the objections of people who pointed out that it had no scientific value whatsoever. He wrote about it afterwards. Everyone you have ever heard of. Every king and every peasant. Every parent, every child, every saint, and every criminal in the history of our species. All of them lived out their entire lives on that dot. The cameras were switched off shortly after to conserve power. It was the last photograph Voyager 1 ever took. It carries a gold-plated record. Greetings in 55 languages. Birdsong, thunder, a mother's kiss, a piece of Bach. Instructions etched on the cover explaining how to play it, drawn for a reader who shares no words with us and may not share eyes. Nobody expects anyone to find it. That was never really the point. The point is what it says about us. A species a few 100,000 years old, on one small world, at the bottom of one gravity well, built a thing and pushed it out past the edge of its own star's territory. And put a song on it. So the lamp we live inside is 37 billion kilometers wide, and we know that because we sent something to the edge and it told us. But now the latter does something it hasn't done yet. Because the next step is not larger by a little. It's larger by 10 times. It is not a place. It is not a boundary. And it is not made of anything you could stand on or fly through. It's a shadow, 5.7 billion light years from here, with the mass of 66 billion suns. TON 618. The name comes from a survey catalog, Tonantzintla 618, an entry in a list of blue objects photographed from an observatory in Mexico in the 1950s. For decades, it was filed as a faint blue star of no particular interest. It is not a star. It is the brightest kind of object in the universe, seen from far enough away to look dim. At the center of a distant galaxy, matter is falling into a black hole. As it falls, it forms a disk, and as the disk spirals inward, it heats through friction until it glows with the output of hundreds of galaxies combined. That glow is called a quasar, and it is how we found this thing at all, not by seeing the black hole, which is invisible, but by seeing the light of everything screaming as it goes in. From that light, astronomers measured the mass. 66 billion times the mass of our sun. Take a moment with the shape of that number, because the earlier steps have prepared you for it in a way you may not have noticed. The sun holds 99.86% of everything in our solar system. Every planet, every moon, every comet, all of it rounding error. Now stack 66 billion of those suns into one object. Every star in a small galaxy. All of it. In one place, in one thing, with one gravity. And here is where it turns strange. That mass creates an event horizon, the boundary past which nothing, not even light, has a path back out. For TON 618, that boundary is about 2,600 times the distance from the Earth to the Sun. Put it where our Sun is. The horizon doesn't stop at Neptune. It doesn't stop at the heliopause, where Voyager crossed. It swallows the entire domain of our star, 43 times over. Voyager 1 has been flying for nearly 50 years and has covered less than 1/20th of the radius of that shadow. Light itself needs about 15 days to cross it. 15 days. The fastest thing that exists, moving at 300,000 kilometers every second, without pause, for 2 weeks, just to get from one side of the darkness to the other. It's worth a moment on how anyone weighs something that far away and that invisible. Spread a quasar's light into a spectrum, and you find broad emission lines, light from gas clouds whipping around the black hole. The faster they move, the more the lines smear. Measure the smear, and you have their speed. Combine that with their distance from the center, and gravity gives you the mass of whatever is holding them. It is the same logic Leverrier used on Uranus, 7 rungs and 170 years ago. Watch how something moves, and deduce what is pulling it. The number that came back sat for years at the top of every list of measured black holes, and it carries real uncertainty. Masses derived this way typically come with error bars of tens of %. And then the part that unsettles people who expect black holes to be violent. If you drifted toward the horizon of something this large, there would be no tearing. The tidal forces at the edge of a black hole this massive are gentler than the gravity you feel lying in your bed right now. You would cross the boundary whole, conscious and entirely intact, and you would not notice the moment it happened. There is no membrane. There is no sound. There is only a line defined by geometry, which you are on one side of and then the other. Nor is the inside crowded. Almost all of that mass sits at a single point at the center. The rest is empty. Hundreds of billions of kilometers of nothing at all, dark and quiet, which you would fall through, alone, for weeks before anything happened. Every step on this ladder so far has been a thing that shines, or a space held open by something that shines. This is the opposite. This is the lamp turned inside out, the one place where light arrives and does not leave. Everything falling in gives up its last brightness at the edge, and the object itself stays perfectly, permanently dark. Which brings us to the reason this step matters more than its size. TON 618 is the heaviest single object on our entire ladder. Nothing above it, not the nebulae, not the clusters, not the great walls of galaxies, is anywhere near this dense or this concentrated. If the question tonight were, what is the most massive thing in the universe, we could stop here and go to sleep. But that isn't the question. And this thing, for all its 66 billion suns, is only step 8 of 20. Because mass and size stopped traveling together at this exact point on the climb. From here on, everything larger is emptier. The things ahead are not heavier than this. They are thinner, colder, more spread out, held together loosely or not at all, and every one of them is bigger. The next one is a shell of ice and dust, and it wraps around everything we have looked at tonight. 270 degrees below zero, and it never changes. No day, no season, no weather of any kind, in any direction, for as long as you care to wait. Out past Neptune, past the heliopause, past the place where Voyager crossed the boundary, there is thought to be a shell of frozen material surrounding the entire solar system in every direction. Not a disk, not a ring, but a sphere. Billions, possibly trillions of icy bodies drifting in the dark, so far from the sun that it appears as just another bright star among the rest. This is the Oort cloud, and its outer edge is estimated at somewhere around 100,000 times the Earth-Sun distance, which makes the full width of it about 200,000 times that distance, roughly 1.5 light-years across. We have crossed a threshold there, quietly. Every measurement until now has been in kilometers, or in multiples of our distance from the Sun. From this step onward, those units stop being useful. We now measure in light years because nothing smaller keeps the numbers readable. Here is what that does to Voyager. The spacecraft that crossed the edge of the Sun's wind after 35 years of flight, that has been traveling since 1977 at 17 kilometers per second, will need roughly 300 years just to reach the inner boundary of this shell, and about 30,000 years to come out the other side. 30,000 years. Our species built its first cities around 6,000 years ago. Voyager will still be inside the Oort cloud, still coasting, when a span 5 times the length of recorded civilization has passed. That is the size of the front garden. Let yourself drift out there for a moment, since it costs nothing. The Sun, from that distance, is no longer a disk. It is a point, the brightest point in the sky, brighter than anything else by a wide margin, but a point all the same. You could cover it with the head of a pin held at arm's length. There is no warmth from it. There is no day. The temperature is a few degrees above absolute zero, and it does not change, ever, in any direction, for as long as you wait. Around you, if you could see them, are chunks of ice and dust, most no larger than a mountain, separated from each other by distances comparable to the width of the entire planetary system. The Oort cloud is called a cloud, and the word is deeply misleading. If you were standing on one of those icy bodies, the nearest of its neighbors would almost certainly be invisible. You would report that you were completely alone, in the dark, in a place with no weather and no seasons and no sound. And every so often, every few million years, on average, something disturbs one of them. A passing star drifts near enough for its gravity to tug. The tug is gentle, almost nothing, but it's enough to change the orbit of one icy body from a slow circle into a long fall. And then that object begins the journey inward, taking tens of thousands of years, gathering speed, until eventually it rounds the Sun, grows a tail of vapor and dust in the sudden heat, and is briefly visible from Earth as a comet. Hale-Bopp, which hung in the sky for 18 months in 1997 and was seen by more people than any comet in history, came from out there. It will return in roughly 2,500 years. So the shell is not entirely silent. It sends us things. It just does it on a schedule where a single message takes longer than recorded history to arrive. There is something worth saying plainly here, though, because it's easy to lose in the numbers. Nobody has ever seen the Oort cloud. Not one object in it has been directly imaged in place. It is inferred, worked out from the behavior of long-period comets, the ones that fall in toward the Sun on enormous orbits, arrive once, and leave for thousands of years. Trace those orbits backward, and they come from all directions, from roughly the same distance. Something out there is releasing them. So this step on the ladder is a conclusion, not a photograph. It's one of the most confident conclusions in the field, and it is still a conclusion. The map has a region on it labeled from evidence rather than sight. And here is the thought that makes this step worth its place tonight. Everything we have climbed through so far sits inside this shell. The walk around the world. The storm on Jupiter. The burning of the sun, the swollen dying giants, the whole 9 billion kilometer spread of the planets, the frontier Voyager crossed. Every one of them inside. All of it wrapped in a sphere of ice and quiet, 1.5 light years wide. And that entire sphere belongs to one star. One. A single, unremarkable, middle-sized yellow lamp with a dark shell drawn around it at a distance no human machine will cross in the lifetime of our species. Now hold that image and consider what the sky is. Because there are between 100 and 400 billion stars in our galaxy. And if what we understand is right, a great many of them are wrapped in shells like this one, of their own. The next step doesn't go to another star. It goes to the room where stars are made, where thousands of them are forming at once, out of a single cloud, 1,300 light years from your window. 1,344 light years from your window. Go back to Orion, the same constellation, the same 3 stars in a row. Below that belt hangs a short line of fainter stars, drawn on old charts as the hunter's sword. Look at the middle one on a dark night, and it will not look quite right. It doesn't hold a sharp point. It smudges. That smudge is the Orion Nebula, and it is the closest place to Earth where stars are being born in large numbers. It measures about 24 light years across, which means light, which needed 15 days to cross the shadow of TON 618, and 30,000 years of Voyager's travel to escape our own icy shell, needs 24 years simply to get from one side of this cloud to the other. Inside it are around 2,000 young stars. Not 2,000 stars scattered across a galaxy. 2,000 forming together in one cloud, in a region small enough that we can photograph the whole of it in a single frame. The mechanism is worth walking through slowly, because it explains every lamp we've looked at tonight, including ours. A cloud of gas and dust drifts in space, cold and thin, thinner than any vacuum manufactured on Earth, but spread across light years, so the total material is enormous. Somewhere in it, a region becomes slightly denser than its surroundings. Gravity, which never stops working and never needs a reason, pulls a little more material toward that spot. The spot gets denser. It pulls harder. Given enough time, and there is always enough time, the center of that clump becomes so compressed that the temperature climbs past 10 million degrees, and hydrogen begins fusing into helium. A star switches on. That is the entire event. No ceremony. A cold cloud collapses under its own weight until the middle of it catches, and then there is light where there was none, and it will keep burning for millions or billions of years. The Orion Nebula is that process, happening 2,000 times over, close enough for us to watch. And when the Hubble Space Telescope looked at it carefully, it found something that changes how the whole climb feels. Around many of those newborn stars are flattened disks of dust and gas. Proplyds, they were named. Solar systems in the earliest stage of assembly. Planets that do not exist yet, in the process of becoming possible. Our own sun formed in a place like this 4.5 billion years ago in a cloud that has long since dispersed. The material that became Earth, the iron in the core, the water in the oceans, the calcium that is currently in your bones, was in a disk like the ones in those photographs, before it was anything else. This is the room where lamps are made. And every step below it on tonight's ladder came out of a room like this one. It's worth stopping on those disks a little longer because of what they imply about the ladder we've been climbing. A proplyd is a flattened ring of gas and dust orbiting a newborn star, typically a few hundred times wider than the distance from the Earth to the Sun. Inside it, dust grains collide and stick. Pebbles become boulders. Boulders become bodies large enough to hold onto each other by gravity, and those bodies sweep up everything remaining in their orbital lane until what's left is a set of separated worlds moving in near circles around a central lamp. That process took our own system somewhere between 10 and 100 million years, a long time by any human measure, and a rounding error against the age of the Sun. Which means that when you look at the Orion Nebula, you are not looking at something exotic. You are looking at the first two rungs of tonight's ladder being assembled, 2,000 times over, in real time, 1,300 light-years away. Somewhere in that cloud, there is very likely a disk that will become a planet with an ocean. Nobody will be watching when it does. There is also a quiet correction to make about what you see when you look at it. If you were flying through the actual nebula, you would see very little. The gas is thinner than any vacuum we can manufacture. Up close, it would be nearly transparent. You could pass straight through the most photographed cloud in the northern sky and notice almost nothing except that a few stars looked slightly dimmed. The nebula is a structure you can only see by being far enough away and by looking for long enough, which has been true of nearly everything tonight. There's one more thing about this nebula that belongs here. It is glowing, and it isn't glowing by itself. At its heart sit 4 hot young stars called the trapezium, and their ultraviolet light is what makes the surrounding gas shine. But that same radiation is also blowing the cloud apart, carving it hollow, stripping material from the very proplyds it illuminates, dismantling the nursery. Over the next few 100,000 years, the Orion Nebula will fade. The gas will disperse. What will remain is a loose cluster of stars, drifting apart, carrying no memory of the cloud that made them. The room takes itself down once the lamps are lit. And that is what the next step is. Not a nursery, but the aftermath, a family of stars that formed together long ago, still holding on to each other, packed so tightly that if you stood on a world inside it, night would never fully arrive. In 1677, a young Edmund Halley was on the island of St. Helena in the South Atlantic, cataloging stars visible from the southern hemisphere that European astronomers had never properly recorded. In the constellation Centaurus, he found an object that had been listed as a star since the time of Ptolemy, 1500 years earlier. He looked at it and recorded that it was not a star. It was a nebula, a smudge, something extended, something with width. He was right, and the reason he was right took another 2 centuries to understand. Omega Centauri is a globular cluster, a roughly spherical swarm of stars bound together by their own gravity, orbiting our galaxy like a satellite. It contains something in the region of 10 million stars, packed into a ball about 150 light-years across. 10 million. In a space 6 times wider than the shell around our own sun. Here's what that density means, and it's the detail worth carrying out of this chapter. Where you live, the nearest star to the sun is Proxima Centauri, 4¼ light-years away. That's the standard spacing in this part of the galaxy, a few light-years between neighbors, which is why our night sky is mostly black, with points scattered thinly across it. In the core of Omega Centauri, stars sit roughly 1/10 of a light-year apart, 40 times closer. Some estimates put the very center tighter still. Stand on a world inside that cluster and look up. You would not see a scattering of pinpricks. You would see hundreds of stars burning as brightly as our full moon, spread across the whole sky in every direction, and thousands more behind them. The ground would carry shadows all night. Reading outdoors at midnight would be effortless. There would be no season, no hour, no weather in which the sky went properly dark. An entire civilization could grow up there without ever developing the word night as we mean it. That density has a consequence that doesn't happen anywhere else in our sky. In the crowded core, stars sometimes pass close enough for gravity to strip material from one onto another. The evidence shows up as blue stragglers, stars that look far younger and hotter than they have any right to be in a cluster this ancient. They were refueled, 2 old stars merging, or one pulling fresh hydrogen off a neighbor and reigniting as something that appears to have been born long after everything around it. Stars that got a second life, purely because they happen to live somewhere crowded. You can see the cluster yourself if you are ever far enough south. From the southern hemisphere, on a dark night, Omega Centauri is visible to the unaided eye as a fuzzy star of about 4th magnitude. The same smudge Halley cataloged in 1677. Sitting there in plain sight, 10 million suns wide, looking like nothing much at all. And these are old lamps. The stars in Omega Centauri are estimated at around 11.5 to 12 billion years old, formed when the universe itself was young, perhaps 1/10 of its current age. They have been circling together since before the Earth existed, before the sun existed, before the cloud that made the sun had gathered. There's a further wrinkle, and it's the kind that makes this object more interesting rather than less. Omega Centauri does not behave quite like a normal globular cluster. Its stars have a wider range of chemical compositions than they should if they had all formed from one cloud at one time. It is far more massive than typical clusters, and it appears to rotate in a way that ordinary clusters don't. It is still classed as a globular cluster. That is what it looks like and how it behaves today. The question is where it came from. The leading explanation is that it did not begin as a cluster at all. It may be the surviving core of a small galaxy that came too close to the Milky Way long ago and was stripped of its outer stars, leaving only the dense center still bound together. If that's right, then what Halley cataloged as a smudge is the last remaining heart of a galaxy, our own Galaxy 8. Which tells you what has been sitting above this entire chapter without being named. 10 million stars, held in a sphere 150 light-years wide, moving as a single object, and that whole object is in orbit. It goes around something. It is a satellite, the way the moon is a satellite, held by something so much larger that a cluster of 10 million suns is merely a detail circling its edge. You have seen that thing your entire life, on any clear night away from streetlights, though you have never once seen the shape of it. You couldn't. You're inside it. You're inside it. Walk somewhere genuinely dark on a clear night, no town on the horizon, no moon, and let your eyes adjust for 20 minutes. A band of pale light will slowly resolve across the sky, running from one horizon to the other. Not a cloud. It doesn't move. It has structure, mottled and uneven, with darker lanes cutting through it. Every culture that ever lived under a dark sky noticed it and named it. A river, a road, a spill of milk, a path the dead walk. What you are actually looking at is the disk of our galaxy, seen edge-on from a position inside it. The pale light is the combined glow of hundreds of billions of stars, too far away and too numerous to separate. The dark lanes are clouds of dust blocking the light of what lies behind them. The Milky Way is about 100,000 light-years across, which means light, the fastest thing there is, which crossed the shadow of TON 618 in 15 days, and the Orion Nebula in 24 years, needs 100,000 years to travel from one edge of our galaxy to the other. Inside that disk are somewhere between 100 and 400 billion stars. The range is wide because counting them is genuinely hard. Most stars are faint red dwarfs, and enormous regions are hidden behind dust. Take the lower figure. 100 billion. Count one star every second, without stopping to sleep or eat, and you would finish in about 3,200 years. Start at the building of the first pyramids, and you would still be counting today. Our sun sits about 27,000 light-years from the center, roughly halfway out in a minor spiral arm. Not the crowded core, not the sparse edge. A quiet suburb. And it is moving. The entire solar system, the sun, the planets, the Oort cloud, all of it, is orbiting the galactic center at roughly 230 kilometers per second and completes one lap every 230 million years. That figure deserves a pause. The last time our solar system was in this part of the galaxy, dinosaurs had not yet appeared. 1 galactic year ago, the continents were arranged differently, and almost nothing alive today had evolved. The Sun has made about 20 such laps in its entire existence. At the center of all of it is Sagittarius A, a black hole of about 4 million solar masses, which is worth setting against step 8. TON 618, 66 billion solar masses is more than 16,000 times heavier than the black hole anchoring our entire galaxy. Our monster is a minor one. We are also still filling in its shape. The Gaia spacecraft measured the positions of nearly 2 billion stars under 1% of the galaxy and found that the disk is not flat. It is warped at the edges, curling up on one side and down on the other, with ripples running through it, the wake of smaller galaxies that passed through and were absorbed long ago. Our galaxy has been eating its neighbors for billions of years, and the evidence is still vibrating in the floor. Now, the part that took the longest to work out, and it is the reason this chapter has a person in it. For most of history, and well into the 20th century, people assumed the Sun sat at or near the center of the star system. It was the natural assumption. Look up, and the sky appears roughly the same density in every direction. In 1918, Harlow Shapley took a different approach. Rather than counting stars, he mapped globular clusters, objects like Omega Centauri, and measured their distances. And he found that they were not distributed evenly around us. They were overwhelmingly concentrated toward one part of the sky, in the direction of Sagittarius. If the clusters orbit the center of the galaxy, and the clusters are all off to one side, then the center is off to one side. We were not in the middle. We were 27,000 light-years out in the suburbs, and nobody had known. That single realization moved humanity's address for the second time. Copernicus took us out of the center of the solar system. Shapley took us out of the center of the galaxy, and it was done by carefully measuring the distances to smudges. So this is our galaxy. 100,000 light-years wide, a few 100 billion stars, one modest black hole at the middle, and our own lamp somewhere out in the quiet part. For a while, this was thought to be everything. The Milky Way was the universe. It isn't. And it isn't even especially large as galaxies go. There is a single galaxy, about 1 billion light-years away, so much wider than ours that its most commonly quoted size is a number that turns out not to be true, and the story of that number is worth stopping the climb for. Type the largest galaxy in the universe into any search bar, in any language, and you will get the same answer almost everywhere. IC 1101, a giant elliptical galaxy roughly 1 billion light-years away. And with it, a figure that appears again and again, 4 to 6 million light-years across. That number is repeated in articles, in videos, in classroom slides, in comment sections. It has been copied so many times that it has taken on the texture of a fact. It is not so much wrong as unanchored. Let me be careful here, because the correction is not that IC 1101 is small. It isn't. It is an enormous galaxy by any reasonable standard. The correction is that the figure depends entirely on where you decide the galaxy ends, and the widely quoted number uses a boundary nobody applies to any other galaxy. Galaxies do not have edges. This is the root of the whole problem. A galaxy's stars thin out gradually, with distance from the center, fading into the background rather than stopping at a boundary. So to state a size at all, astronomers have to choose a definition, most commonly the isophotal diameter, meaning the width out to a specified level of surface brightness. It's a convention, and it's applied consistently so that galaxies can be compared with each other. Measured that way, IC 1101 comes out at roughly 400,000 light-years across. 400,000, not 4 million. About 4 times the width of the Milky Way, genuinely one of the largest galaxies known, and roughly 10 times smaller than the number in circulation. So where did the millions come from? 2 places, both of them understandable, and both of them the sort of error that survives because it makes a better headline. The first is the halo. Around IC 1101, there is a vast, extremely faint envelope of stars and light, extending far past the region where the galaxy is conventionally measured. If you count that halo, and if you use certain older distance assumptions, you can produce numbers reaching into the millions of light years. But that diffuse glow is not the galaxy in the sense that any other galaxy's size means. Apply the same generous treatment to the Milky Way, and our own figure would balloon too. The second is the cluster. IC 1101 sits at the center of Abell 2029, a rich galaxy cluster. And that structure genuinely does span something like 5 to 8 million light-years. It's easy, in a chain of copied summaries, for the size of the cluster to migrate quietly onto the galaxy sitting in its middle. So the widely repeated figure is roughly the size of the cluster, wearing the name of the galaxy. Here is why I am spending a chapter of a sleep video on a measurement dispute. Because tonight's entire climb rests on numbers being comparable. If one rung of the ladder is inflated by a factor of 10, the whole shape of the thing is wrong, and you would have no way to feel that anything had gone crooked. The steps would still sound impressive. They would simply be lying about the relationship between each other, which is the only thing this ladder is actually made of. And this particular case is instructive, because it shows how these things spread. Nobody invented it maliciously. Someone applied a generous boundary once, someone else quoted the figure without the boundary attached, and after enough repetitions, the caveat stopped traveling with the number. That is how most confident-sounding numbers lose their meaning. Not by lying. By copying without the conditions. There's a simple test that makes the whole thing obvious, and you can run it in your head from where you're lying. Our own galaxy has a faint stellar halo too, a sparse cloud of old stars and globular clusters extending far beyond the bright disk, plus a dark matter halo reaching further still. If we measured the Milky Way, the way the inflated figure measures IC 1101, our galaxy's quoted size would jump from 100,000 light-years to several hundred thousand, possibly more. Nobody does that because it would make our galaxy incomparable with every other galaxy in every catalog. The convention exists precisely so that the numbers mean the same thing from one object to the next. Apply one standard to everything, and IC 1101 is about 4 times our width. Apply a generous standard to one object and a strict standard to everything else, and you have manufactured a champion. IC 1101 does not need the inflation. 400,000 light-years of stars. A central black hole among the most massive ever estimated. The heart of a cluster of thousands of galaxies, glowing with the light of something like 100 trillion suns, and forming almost no new stars because it burned through its cold gas long ago. It is a vast, ancient, dying thing. It just isn't 6 million light-years wide. And notice what happened to the latter while we were arguing. We have moved from one galaxy to a galaxy sitting inside a cluster of thousands. The step after a galaxy is not a bigger galaxy. It's what happens when galaxies stop being counted individually, when they gather, and the gathering becomes the object. There is such a gathering directly around us. We live in one, and the nearest large member of it is visible to your naked eye tonight, if the sky is dark enough, a faint oval smudge that, for most of human history, everyone assumed was a small cloud inside our own galaxy. Until one night in 1923, when a man at a telescope crossed out what he had written on a photographic plate and wrote one word above it. On the night of the 5th of October 1923, Edwin Hubble was using the 100-inch telescope on Mount Wilson to photograph the Andromeda Nebula, at that time believed by many astronomers to be a cloud of gas within the Milky Way. He was looking for novae, stars that flare suddenly and fade. On the plate he catalogued that night, he marked 3 candidates with the letter N. When he compared it against earlier plates, one of those objects turned out not to be a nova at all. It was brightening and dimming on a regular cycle, a Cepheid variable, a type of star whose pulsation period is directly tied to its true brightness. That relationship, worked out by Henrietta Swan Leavitt a decade earlier, turns such a star into a measuring rod. Time the pulse, and you know how bright the star truly is. Compare that to how bright it appears, and you have its distance. Hubble crossed out the N on the plate and wrote, in ink, above it, VR. That plate still exists. You can see the crossed-out letter and the exclamation mark in his handwriting, and it is one of the few moments in science where you can point at the physical object and say, here, this is where the universe changed size, because the distance came out at roughly 900,000 light-years, later revised upward, and now measured at about 2.5 million. The Milky Way is 100,000 light-years across. Whatever Andromeda was, it was far too distant to be inside it. It was another galaxy, which meant the smudges were all galaxies, which meant the Milky Way was not the universe, but one object among an unknown number of others, and the size of everything jumped by a factor nobody could yet state. That happened within the lifetime of people whose grandchildren are still alive. Andromeda itself is larger than our galaxy. around 150,000 to 220,000 light years across, depending on where you draw the line, holding perhaps 1 trillion stars. It is the most distant object the unaided human eye can see. The light landing on your retina from it left before our species existed, and it is coming toward us at about 110 kilometers per second. In roughly 4 billion years, the two galaxies will meet. Not collide in the way the word suggests. The stars are so widely spaced that almost none will actually strike each other. The galaxies will pass through one another, tear each other's structure apart with gravity, throw long streams of stars out into the dark, fall back together, and eventually settle into a single larger elliptical galaxy with no spiral arms left. Any world still orbiting a surviving star would see a night sky utterly transformed over hundreds of millions of years without a single dramatic moment in the whole process. There's a detail in that story that usually gets left out, and it belongs here more than the telescope does. Hubble could make that measurement because of work done a decade earlier by Henrietta Swan Leavitt at Harvard College Observatory. She was employed as a computer, one of a group of women hired to measure and catalog stars on photographic plates, paid by the hour, and generally not permitted to operate the telescopes whose plates they analyzed. Working through thousands of variable stars in the Magellanic Clouds, she noticed that the brighter ones took longer to complete their cycle of brightening and dimming, and that the relationship was regular enough to be written as a law. That law is the reason distance can be measured at all beyond our immediate neighborhood. Every rung above this one on tonight's ladder, every galaxy, every cluster, every wall, is placed using a chain of measurement whose first link is her work. She died in 1921, 2 years before the plate with VAR. Written on it, Andromeda itself is worth a moment on its own terms, too. If your eyes could gather light the way a long exposure does, it would not look like a smudge. It would be an oval, roughly 6 times the width of the full moon, stretched across a serious portion of the night sky. It is that large from here. We simply cannot collect enough of its light in a fraction of a second to see anything but the bright core. The thing you glimpse as a faint blur is the small central piece of an object that, if we could see all of it, would dominate the sky. Together, the Milky Way, Andromeda, the Triangulum Galaxy, and more than 50 smaller companions form the Local Group, a gravitationally bound collection about 10 million light-years across. That is our address at this rung. Not one galaxy. A neighborhood of them, bound together, drifting as a unit. And here, the ladder does something it hasn't done before. Because there is a single galaxy out there, one object, with one host, that is larger than this entire neighborhood of 50. In 2022, astronomers working with a radio telescope array in the Netherlands published something that sounds, at first hearing, like a category error. They had found a structure 16 million light-years across, powered by a single, ordinary-looking galaxy. They named it Alcyonius, after a giant from Greek mythology. The Local Group, our galaxy, Andromeda, and 50-odd companions, is about 10 million light-years wide. This one object belonging to one galaxy is more than half again as large as all of that. Here is how something like that is possible, and the mechanism is the reason this step earns its place on the ladder. At the center of the host galaxy is a supermassive black hole. Material falling toward it forms a disk. As that disk spins, magnetic fields wind up and fling a fraction of the infalling matter straight back out along the rotation axis. Two narrow jets of plasma, launched in opposite directions at close to the speed of light. Those jets travel outward, far beyond the stars of the galaxy that made them, until they slow against the thin gas between galaxies and spread into enormous lobes of glowing radio-emitting plasma. The galaxy itself is unremarkable. Its stellar body measures a little under 250,000 light-years across, comparable to Andromeda, and the structure it has blown outward reaches roughly 70 times further than that. You will sometimes see this quoted as 160 times the size of the Milky Way, which is also true, and is a different comparison. It measures the lobes against our galaxy, not against the galaxy that produced them. Both numbers are correct, and they answer different questions, which is exactly the sort of thing that turns into a wrong fact after 3 or 4 rounds of copying. The timescale involved is its own kind of vast. Those lobes did not appear. They were inflated slowly, over something like 100 million years of continuous output. A jet firing without interruption for longer than mammals have existed on Earth, pushing material outward at a pace that would look like nothing at all if you watched for a human lifetime. And the engine may already have switched off. Black holes go quiet when the supply of infalling material thins out, and the lobes keep glowing for a long time afterward on stored energy, like a room that stays warm after the fire has gone out. What we're seeing may be the afterglow of a process that finished before our species learned to write. There is also a reason this object was found only recently, and it says something about how the map of the universe actually gets drawn. Alcyonius is faint. Extremely faint. The signal is spread over such an enormous area of sky that any individual patch of it is barely above the noise, which is why generations of radio surveys passed straight over it. It took a telescope array designed for low frequencies, combined with processing that deliberately looked for large, diffuse, low-brightness structure rather than bright, compact sources before it appeared in the data. It had been there the entire time. Nobody had asked the sky the right question. That is worth carrying into the last stretch of the climb, because the remaining rungs were all found the same way, not by looking harder at one point, but by stepping back and asking about the arrangement of everything at once. There is nothing dramatic to see. Alcyonius is invisible to the eye and invisible to optical telescopes. It emits at radio wavelengths, and the plasma filling those lobes is thinner than the best vacuum any laboratory on Earth can produce. If you were somehow placed inside one of them, you would notice nothing whatsoever. No glow, no heat, no resistance. You would report that you were in empty space, and you would be very nearly right. That is what makes it the perfect hinge for tonight's climb. Because up to step 8, we measured things by how much material they contained. Then, gradually, we started measuring things by how far they reached. And here, the two definitions come apart completely. Alcyonius contains almost nothing. Its lobes are emptier than emptiness, made of scattered particles and magnetic field. And it is 16 million light-years across, larger than the local group, larger than any galaxy, larger than everything we have looked at tonight. Large no longer means full. From here on, it means far-reaching, which is a good thing to have learned right now, because the remaining 5 steps are all like this. Structures held together by gravity across distances that make Alcyonius look local. Regions defined not by what is in them, but by how everything inside them is moving. And one of them, the strangest step on the whole ladder, is defined by nothing being there at all. Defined by nothing being there at all. We'll get to that one. First, the opposite, the most crowded place we have looked at tonight, and the photograph that came out of it. About 53 million light-years away sits M87, a giant elliptical galaxy at the heart of the Virgo cluster. It holds several trillion stars in a featureless glowing ball, with no spiral arms and almost no new star formation. It stopped making lamps a long time ago. At its center is a black hole of about 6.5 billion solar masses. On the 10th of April, 2019, a photograph of that black hole was released to the world. Not an artist's impression, not a simulation. An image assembled from measurements of the shadow cast by an object from which no light escapes. The way it was done is worth telling slowly, because it is one of the more improbable things our species has managed. A black hole's shadow, at that distance, is unimaginably small in the sky, comparable to trying to read a newspaper on the surface of the moon. No telescope on Earth is remotely large enough. To resolve something that fine, you would need a dish the size of the planet. So they built one. 8 radio observatories on 4 continents: Chile, Hawaii, Arizona, Mexico, Spain, and the South Pole, observed the same target at the same time. Each recorded the incoming waves with atomic clock timing precise enough that the signals could later be combined as though they had all arrived at one instrument. The technique gives you a telescope as wide as the distance between the dishes. The Earth itself became the lens. The data was too large to send over any network. Petabytes of it, recorded on stacks of hard drives, physically flown to 2 processing centers. The drives from the South Pole Station could not leave until the Antarctic winter ended and flights resumed, so part of the observation sat on a frozen continent for months before anyone could look at it. Then came 2 years of analysis, run by independent teams working deliberately blind to each other's results, so that nobody could unconsciously steer the outcome toward the picture everyone expected. And what emerged was a ring of light around a dark center. Slightly brighter on one side, because the material on that side is rotating toward us, and its light is boosted. Almost exactly the shape and size predicted by general relativity a century earlier for a black hole of that mass. Take the emotional measure of that for a moment. At this hour, lying wherever you are, Einstein published the equations in 1915. He is reported to have doubted that black holes could physically exist. 104 years later, a group of humans on a small planet pointed enough machines at the sky in enough places at the same time and got back a picture of one, and it looked the way the mathematics said it would. There is an older detail about M87 that fits this chapter, and it predates all of that technology by a century. In 1918, Heber Curtis, observing from Lick Observatory, noticed a straight ray of light extending from the center of M87 out into the surrounding dark. He described it as a curious straight ray and could offer no explanation for what it was. It is a jet, the same phenomenon we met at Alcemaeus, plasma flung from the neighborhood of the black hole at nearly the speed of light. This one extends roughly 5,000 light-years from the galactic core, and it is bright enough that it was visible on photographic plates more than 30 years before anyone had proposed that black holes might physically exist. So the first evidence of the object photographed in 2019 had been sitting in an observatory logbook since the end of the First World War. Nobody could read it yet. Now widen out, because M87 is not the point of this rung. M87 is the anchor of the Virgo cluster, over 1,000 galaxies, bound by gravity, filling a region tens of millions of light-years across, all swimming in a haze of gas, heated to tens of millions of degrees. And the Virgo cluster is itself the central node of the Virgo supercluster, a structure roughly 110 million light-years wide, of which our own local group is one small outlying member. Which means, quietly, that our address just gained another line. Earth, solar system, Milky Way, local group, and now the outskirts of a supercluster whose gravitational center is 50-odd million light-years away and pulling. That's where the latter is heading now, into structures so large that they are described less by what they contain than by which way everything inside them is moving. But before that, there is one more step, and it is unlike every other rung tonight. Because so far, every single thing we have measured has been a thing that is there. Around 60, that is how many galaxies have been found in a region that should contain roughly 2,000. In 1981, a survey led by Robert Kirshner mapped the distances to galaxies in the direction of the constellation Boötes and found a region where there were essentially none. Not fewer than average. Almost nothing at all. The Boötes Void is roughly 330 million light-years across, centered about 700 million light-years from here. Based on how galaxies are distributed in the rest of the observable universe, a sphere that size should contain something in the region of 2,000 of them. Around 60 have been found. Try to hold the shape of that. This is not a small gap between galaxies. It is a bubble of near nothing more than 3,000 times wider than our galaxy, in which almost every lamp that should exist does not. And here is the number that fixes it in place. It takes light 330 million years to cross it. Anything traveling more slowly, which is everything, could set out across that emptiness and, over a span longer than the entire age of complex life on Earth, still not reach the other side. There's an observation attached to this void that has stayed with astronomers, and it belongs in a video about scale. If our own galaxy happened to sit at the center of the Boötes Void, the sky would look very nearly empty. The nearest large galaxies would be so distant and so faint that we would not have found them with early telescopes. It has been suggested that we would not have known other galaxies existed at all until well into the 20th century. We would have grown up believing the Milky Way was everything. Not through any error of reasoning, simply because we would have been standing somewhere the evidence wasn't. That is not a comfortable thought, but it is a useful one at this hour. What a civilization is able to know depends partly on where it happens to be sitting. Voids are not accidents, and they are not holes punched into something. They are the natural result of how structure forms. Start with a universe that is almost, but not perfectly, uniform. Some regions begin very slightly denser than others. Gravity pulls matter from the thinner regions toward the denser ones. The thin regions get thinner. The dense regions get denser and eventually collapse into filaments and clusters. Run that forward for 13 billion years, and you don't get an even scattering. You get walls and threads of matter surrounding expanding hollows, because everything that was in the hollows has spent the entire history of the universe walking out of them. A void is the shape left behind by matter that has already gone somewhere else. The Boötes Void isn't perfectly empty either, and the way it isn't is interesting. The few dozen galaxies inside it are not scattered at random through the volume. They appear to lie along a tube running roughly through the middle of it, which some interpretations read as the seam where several smaller voids merged into one, leaving a thin trace of matter along the join. Even the emptiest place we know has structure in it, if you look long enough. Now here is why this rung is the hinge of the whole climb. For 16 steps, we have been measuring presence. A planet, a star, a shell of ice, a nursery, a swarm, a galaxy, a cluster. This step measures absence, and the absence is larger than almost everything we have measured that was made of something. The dark between the lamps is not the background of the picture. It has a shape. It has boundaries. It has a size you can state in light years. It can be mapped and cataloged and given a name. And it turns out the universe is mostly this. Map the distribution of galaxies on the largest scales, and what emerges is not a scattering of matter through empty space. It is a network, filaments and sheets of galaxies, drawn out along the edges of enormous hollow regions, like the film of soap on a mass of bubbles. Most of the volume is void. The bright material is the skin between the emptinesses, which reopens tonight's question in a way that cannot be closed again. If we are asking what the largest thing in the universe is, does a void count? It has a definite size, 330 million light-years, larger than the supercluster we live in. It has a boundary. It has structure. It is a distinct, identifiable region of the cosmos. It simply has nothing in it. I don't think there's a clean answer, and I'd rather leave the question honestly open than pretend otherwise. But notice what has happened to the latter. We are now climbing through things whose size comes from arrangement rather than substance, from how matter is distributed, not how much of it there is. And once that's true, the next question is not what is out there. It's what everything is doing. Because we are moving. Right now, at 600 kilometers a second, and not in a random direction, towards something that has been pulling on our entire region of the universe for as long as it has existed. We cannot see it. It is hidden behind our own galaxy. 600 kilometers every second. That is how fast you are moving right now, in a direction you have never chosen and cannot feel, towards something nobody has ever seen. In 1986 and 87, a group of 7 astronomers, known afterwards, half-jokingly, as the 7 Samurai, published a result that nobody had expected. They had been measuring the motions of hundreds of elliptical galaxies, expecting to find them drifting apart smoothly with the general expansion of space. Instead, they found a large-scale flow. Our galaxy and the local group and thousands of other galaxies across a vast region were all moving together in the same direction at roughly 600 kilometers per second, over and above the expansion. Something with enormous mass was pulling. They called it the Great Attractor, and then ran into a problem that is almost comic in its bad luck. The direction of the pull lies in the constellation Centaurus, which, from our position inside the Milky Way, sits directly behind the dense central plane of our own galaxy. Dust and stars and gas are piled up along that line of sight, absorbing and scattering light, blocking the view of whatever lies beyond. Astronomers call that region the zone of avoidance. It is about 20% of the sky, and for most of the history of astronomy, it was simply unobservable. So the single most significant gravitational feature in our part of the universe, the thing our entire galaxy is falling toward, happens to be located behind the one obstacle we cannot move. We are being pulled by something we cannot look at because we are standing in the wrong place. Over the following decades, X-ray and infrared and radio observations, which penetrate dust far better than visible light, gradually filled the picture in. The Great Attractor turned out to be a concentration of mass associated with the Norma cluster and the region around it. Later work suggested that much of the pull comes from further away still, from an even larger concentration behind it, called the Shapley supercluster. The thing pulling us is layered. There is something behind the something. Then, in 2014, a team led by Brent Tully did something more elegant than measuring mass. They mapped motion. Rather than asking which galaxies are near each other, they asked which galaxies are flowing toward the same place, and drew the boundary where the flow divides. It's the way a watershed is defined on Earth. Not by drawing a line around a mountain range, but by asking which way the rain runs. Mapped that way, our home structure turned out to be far larger than anyone had drawn before, about 520 million light-years across, containing something like 100,000 galaxies, all drifting toward the same gravitational basin. They named it Laniakea. Hawaiian, chosen with help from a language expert, immeasurable heaven. We are on its outer edge, falling inward. It's worth being clear about what that motion is and isn't, because it's easy to picture it wrongly. The universe is expanding, which means that on the largest scales, every galaxy is drifting away from every other. But gravity still works locally, and where matter has piled up, it pulls neighboring matter toward it faster than expansion pushes it away. Those local pulls are called peculiar velocities. Peculiar here meaning particular to that object, not strange. So there are two things happening to us at once. The general expansion is carrying everything apart, and underneath it, our whole neighborhood is falling toward a concentration of mass in Centaurus at 600 kilometers a second. 600 kilometers a second is not a gentle drift. In the time it takes to read this sentence, the Earth, the Sun, and everything bound to them have moved several thousand kilometers in that direction. You have never felt it, and never will, because everything around you is moving with you, the same reason you cannot feel the planet turning, or its orbit, or the sun's 230 million year lap around the galaxy. 4 separate motions, stacked on top of each other, and your body registers none of them. Stillness, at every scale we have visited tonight, is something that only ever appears to exist. There's a quiet consequence in the way Laniakea is defined that fits this hour well. It has no wall. There is no place where the structure stops and something else begins. Only the line where the drift changes direction. Cross it, and you would notice nothing whatsoever, except that everything around you had begun very slowly falling somewhere else. The largest structure we belong to is not a thing with an edge. It is a direction that everything nearby agrees on. And it is not the largest. Beyond the basin we are falling into, the map keeps going, into threads of galaxies strung across such distances that the word structure starts to strain. One of them was named only recently, after a device made of knotted string. A device made of knotted string. The Inca kept records without an alphabet. They used quipu, bundles of cords, hung from a main line, with knots tied at intervals along them. Position, color, knot type, and spacing all carried meaning. Census figures, tribute, calendars, possibly narrative. An accounting system you could roll up and carry. In 2025, a team led by Hans Boehringer published a survey of the largest structures visible in X-ray light, mapping the distribution of galaxy clusters across a large volume of the nearby universe. The biggest thing they found stretched about 1.4 billion light-years and contained around 68 galaxy clusters strung along it. They named it quipu because that is what it looks like on the map, a long main filament with clusters knotted along its length at intervals, like a cord recording numbers. 1.4 billion light-years. Set that against the rungs below it. Our galaxy is 100,000 light-years across, and this is 14,000 times wider. Laniakea, the entire basin we are falling into, would fit across it nearly 3 times. Light leaving one end of Quipu would need 1.5 billion years to reach the other, which is longer than multicellular life has existed on Earth. And it is made of clusters. Not stars, not galaxies, clusters, each one containing hundreds or thousands of galaxies, each galaxy containing hundreds of billions of stars, each star potentially wrapped in a shell of ice, like the one that took Voyager 30,000 years to cross. Every single rung we have climbed tonight is somewhere inside a knot on that cord. The way a thing like this gets found is worth a moment, because it is not what most people picture when they imagine astronomy. Nobody photographed Quipu. There is no image of it, and there never will be. It is far too large to fit in any field of view, and far too diffuse to show up as an object. What exists instead is a catalog. Galaxy clusters are extremely hot in X-ray light because the gas filling the space between their galaxies is heated to tens of millions of degrees by the sheer depth of the gravitational well. That makes clusters visible to X-ray telescopes from enormous distances as faint extended glows. Survey enough sky, measure a distance for each glow, and you can place every cluster in a three-dimensional map. Then you stop looking at individual objects entirely and start looking at the map, asking where the density runs above average and what shape those overdense regions take. Quipu emerged from that. It is a pattern found in a list, and the list took decades of telescope time to assemble. There is something appropriate in the name then, beyond the visual resemblance. A Quipu was also a record, information held in an arrangement rather than in a picture, readable only by someone who knew what the spacing meant. There is a caution to attach here, and it applies to this whole final stretch of the ladder. Structures at this scale are not objects in the way a planet is an object. They are not bound together. The expansion of the universe is stretching them, and over billions of years they will thin out rather than collapse. They are identified statistically, regions where the density of galaxies runs measurably above average, traced across the sky. Which means that their boundaries, and therefore their stated sizes, depend on the threshold a survey chooses to use. Draw the line at a slightly different density, and a structure can grow, shrink, split into two, or merge with a neighbor. That's not a reason to disbelieve them. It's a reason to hold the numbers with the right grip. These are real overdensities in the actual distribution of matter. They are also, in part, artifacts of where we chose to put the line. Quipu was not alone in that survey. The same work identified 5 superstructures of comparable scale, and the numbers attached to them are the real finding. Between them, those 5 occupy about 13% of the volume surveyed and hold 45% of the galaxy clusters, 30% of the galaxies, and 1/4 of all the matter. 1/8 of the space, holding 1/4 of everything in it, which is exactly what the previous rung was showing us from the other side. The bright structures and the hollow ones are the same fact, described from opposite directions. And that caution matters enormously right now, because we have arrived at the last rung. 20 steps ago, we started with a walk around the equator that would take 3 years. Since then, failed stars and dying ones. A shadow with the mass of 66 billion suns. A shell of ice, a nursery, a swarm, a galaxy. A number the whole internet had wrong. 2 jets thrown from a single point, and a photograph of a shadow. An emptiness larger than everything around it, and a basin that everything nearby is falling into. 1 step remains. It is the largest single structure ever identified, and it is the one I have the most reservations about. The largest structure anyone has ever claimed. Notice the wording. Every rung until now has been something we can point at and measure. This one is a proposal, and the proposal is still being argued over, 12 years after it was made. In 2013, Istvan Horvath, John Hakkila, and Zsolt Bagoli were studying the sky distribution of gamma-ray bursts, the brightest explosions in the universe, produced when massive stars collapse or neutron stars merge. Because they are so luminous, they can be detected from enormous distances, which makes them useful markers of where matter is. Working with data largely from NASA's Swift satellite, they noticed something in one region of sky. Of 31 bursts found at a similar distance there, 19 were concentrated into a patch, far tighter than random chance should allow, all of them sitting at a redshift between 1.6 and 2.1, which is to say, all at roughly the same enormous distance. If those bursts trace matter, then that region contains an enormous concentration of galaxies. They named it after the 2 constellations it appears behind, in the direction of Hercules and Corona Borealis, the northern crown. The Hercules-Corona Borealis Great Wall. And it spans roughly 10 billion light-years. There is the answer to the question we started with, some 3 hours ago, with the asterisk I promised you at the beginning still attached to it. So let me give you both answers now, plainly, because you have earned them. The largest structure we can confidently describe is the one we passed on the previous rung, Quipu. 1.4 billion light-years. 68 galaxy clusters, mapped from an X-ray survey, measured with a method that works the same way everywhere. Nobody is arguing about whether Quipu is there. The largest structure anyone has claimed is this wall. 10 billion light-years, 7 times larger. And that is the one still on trial. 10 billion light-years. Think about what light has done tonight. 8 minutes to reach your skin from the sun. 15 days to cross the shadow of TON 618. 100,000 years to span our own galaxy. To cross this, it needs nearly 3/4 of the entire age of the universe. It sits so far away that we see it as it was about 10 billion years ago, when the universe was less than 1/3 of its current age. We are not looking at an object. We are looking at a photograph of a region taken before the Earth existed, and the region has had 10 billion years to change since the picture was taken. Now the part that most retellings leave out. This result is contested, and I'm not going to pretend otherwise at the end of a long climb. The concern is straightforward and serious. Gamma-ray bursts are not detected evenly across the sky. Whether we see one depends on where the satellite was pointing, how much of the sky it had already surveyed, and whether anyone managed to measure a distance for it afterwards. That produces uneven coverage, and uneven coverage can manufacture apparent clumps in the data that do not correspond to real clumps of matter. In 2016, Ukwata and Wozniak examined the statistics and found the distribution consistent with what random simulations could produce, the grouping falling below the usual threshold for calling something real. In 2020, Christian argued that because of biases built into these particular tests, the bar should be set far higher than the standard one, which would leave the original claim short of it. The Discovery team answered. Also in 2020, Horvath and colleagues reran the analysis on the most reliable dataset then available and reported that the clustering was still there. They also said plainly what would settle it: a satellite designed to survey gamma-ray bursts evenly across the whole sky. Theseus is the one usually named. So the honest state of things is a live disagreement between competent people, not a settled fact wearing a confident number. There is also a theoretical objection worth stating plainly. Modern cosmology holds that, on sufficiently large scales, the universe is homogeneous, roughly the same everywhere. Most estimates place the ceiling for coherent structures at a few 100 million to around 1 billion light-years. A 10 billion light-year wall would exceed that limit by an order of magnitude. So either our understanding of how structure forms is missing something significant, or the wall is an artifact of how we happen to look. Both are live possibilities, and the honest position tonight is that this is unresolved. It's worth being precise about what homogeneous on large scales actually means, because it is the crux of the objection. Nobody claims the universe is smooth at small scales. Obviously it isn't. There are planets and stars and galaxies and voids, and we have spent the whole night climbing through them. The claim is that if you zoom out far enough and take a large enough box anywhere in the universe, every box you take will contain roughly the same amount of matter as every other. Surveys suggest that transition happens somewhere around a few 100 million light-years. Below that scale, structure. Above it, sameness. A 10 billion light-year wall would mean the transition is somewhere else entirely, or that the boxes are still coming out uneven at scales where the theory says they shouldn't. That is why the claim received the scrutiny it did. It isn't a dispute about one object. It's a dispute about whether the framework holds, which leaves the question of tonight in a more interesting place than a single answer would have. If the wall is real, it is the largest thing in the universe by a wide margin, and our models of cosmic structure need revising. If it is not, then the largest confirmed structures are the ones we passed on the way here: quipu, the great walls, the filaments of the cosmic web. And the answer becomes something in the range of 1 to 1.5 billion light years. Either way, the shape of the climb holds. And either way, the thing we set out to find behaves exactly the way everything else on this ladder behaved. Because think back to the first rung, and to what Everest became when you shrank the Earth to the size of a billiard ball. Large is not a property a thing owns. It's a relationship between the thing and wherever you happen to be standing. That was true of a mountain. It was true of a planet and of a star that could swallow the orbit of Saturn, and of a shadow that takes light 15 days to cross, and of a galaxy, and of a void with almost nothing in it. It is true of a wall 10 billion light years wide. There is no final rung. There is only the next relationship and the next place to stand. So that was the climb. 20 steps from a world you could walk around in 3 years to a structure that light needs most of the age of the universe to cross. And now there's nothing left to work out. Nothing else to hold on to. This last stretch is only for settling. Let the ladder go, if you like. It has done its job. You don't need to keep any of the numbers. Not the 600 million tons a second. Not the 35 years to the edge of the sun's wind. Not the 10 billion light years. They were never the point. They were just handholds, useful for climbing and fine to release once you are lying still. What's worth keeping is smaller and easier to carry. That the mountains you cannot climb become invisible from a little way off. That the largest fire anything can hold still has a limit and reaches it and lets go of its outer layers gently. That a man once found a planet with a pencil, and a woman's measurement of pulsing stars let another man discover that the smudge in the sky was a galaxy. That we sent one small machine past the edge of everything our star governs, and put a song on it, and did not expect anyone to hear. That we are being pulled, right now, towards something we cannot see, because we are standing in the wrong place to look, and that this is fine, and the pull continues regardless of whether we can watch it. If any of this was a good way to spend the night, you can leave a like or subscribe, and it helps this quiet corner reach someone else who's awake at this hour and would rather be drifting. And if you'd rather not, that's genuinely fine too. Nothing here needed anything from you. Let the climb settle into the shape it wants, without you holding it up. You began standing on something you could walk around, given 3 years and nothing else to do. Then the mountains flattened. Then the world became a marble beside a lamp that had failed to light, and beside one that had. Then the lamps grew until fire could not hold them. A shell of ice you would need 30,000 years to cross. A room where new lamps were being made 2,000 at a time. A swarm so crowded that night never fell. A galaxy you have looked at your whole life without ever seeing its shape because you were inside it. Then the arrangements. Neighbors. Clusters. jets thrown further than everything around them. A hollow big enough to hide the rest of the universe from anyone living at its center. A basin, and everything falling into it, including you, right now, without a sound. And at the end, a wall 10 billion light years wide that might not be there at all. That's the whole ladder. It took the night to climb, and it fits in one breath on the way back down. Now let it all get further away. The lamps are still burning out there. The sun is converting hydrogen into light, while you lie here, exactly as it has for 4.5 billion years, exactly as it will tomorrow. Somewhere in Orion, a cloud is collapsing into a new star that nobody will ever name. Andromeda is drifting closer at a pace that will take 4 billion years to matter. None of it needs you awake for any of it. You are lying inside one lamp, on one small world, on the outer edge of a basin that everything nearby is quietly falling into. That is your address. It is a good one. It is warm, and it is lit, and it is yours. The dark between the lamps has a size too. We measured it tonight. It turns out to be most of everything, and it is not empty in the way people fear. It is simply the space that lets the lights be separate enough to see. So let the dark be that, now. Not absence. Just the room the lamps need. There's no more climbing to do. Everything above you is going to keep being there, at exactly the size it is, whether or not anyone is measuring it tonight. The wall may be real, or it may be an artifact. Nobody listening to this will be alive when that's settled, and the question is in good hands regardless. Somebody is working on it right now, in a building somewhere, with a coffee going cold, and that is a fine thing to be true while you sleep. The Boötes Void is still empty. Quipu is still knotted. Voyager is still coasting, its instruments going out one by one, 22 hours of radio silence between every question and every answer. None of it is waiting on you. Let your breathing slow. Let the numbers go. Let the ladder fold up and be put away. You are small in all of this, and you are not lost. You're one of the lit places. Good night. I'll stay a while longer without words. There's nothing left to follow, just the quiet from out there, for as long as you need it. Sleep well.